Hi, myself Suguna. In this video, we are going to prove the rank-nullity theorem. Statement: let T from U to V be a linear transformation, then R of T plus N of T is equal to dimension of U. That means rank plus nullity is equal to dimension of U. To prove this theorem, let us consider the Venn diagram. Here, we have considered the set U and the set V, and we have defined a transformation T from U to V. And U has elements alpha 1, alpha 2, so on alpha n, beta 1, beta 2, so on beta r. And V has beta 1 dash, beta 2 dash, 0, beta r dash. So let us consider B1 is a basis containing alpha 1, alpha 2, alpha 3, alpha n vectors as a basis of n of t. N of t means it is nothing but the null space. See, inside this represents a null space, and here all the images set together is known as the range of the linear transformation. That is the range space. Range set is a subset of V and null space is a subset of U. Null space means here all the elements are mapped to 0. So by using these results, now let us prove the theorem. Let the basis B1 is equal to alpha 1, alpha 2, so on alpha n be the basis of n of t that we have represented here. Since it is a basis of n of t, images of all these elements, that is image of alpha 1, that is a transformation of alpha 1 is equal to transformation of alpha 2 is equal to transformation of alpha 3, so on transformation of alpha n is equal to 0. And the dimension of n of t is equal to small n of t, or we represent it as small n. The dimension of null space is nothing but nullity. Nullity is denoted as n of t, which is equal to n. Let B2 be the another basis having the vectors beta 1 dash, beta 2 dash, beta 3 dash, so on beta r dash be a basis of r of t. See that we have represented here. So this is r of t and basis B2 containing B1 dash, B2 dash, 0, Br dash, etc. So these elements. This implies that there exists beta 1, beta 2, beta 3, so on beta r in U such that T of beta 1 is equal to beta 1 dash, T of beta 2 is equal to beta 2 dash, so on T of beta r is equal to beta r dash. Beta 1 is related to beta 1 dash, that means T of beta 1 is equal to beta 1 dash, T of beta 2 is equal to T of beta 2 dash, T of beta r is equal to beta r dash. Then T of beta 1 is equal to beta 1 dash, T of beta 2 is equal to beta 2 dash, so on T of beta r is equal to beta r dash. Now let B be containing alpha 1, alpha 2, so on alpha n, beta 1, beta 2, so on beta r, and we show that B is a basis of U. To show that B is a basis of U, we have to prove that B spans U and B is linearly independent, then only B will be the basis of U. First let us show that B spans U. Consider one element alpha belongs to U, then which implies that T of alpha belongs to R of T. Since T of alpha belongs to the range set, then T of alpha can be expressed as the linear combination of its preceding vectors. So T of alpha is equal to D1 beta 1 dash plus D2 beta 2 dash plus D3 beta 3 dash, so on dr beta r dash. D1 beta 1 dash is nothing but T of beta 1. So instead of beta 1 dash and beta 2 dash, let us take them as T of beta 1, T of beta 2, so on. Hence T of alpha is equal to D1 t beta 1 plus d2 t beta 2 plus d3 t beta 3 so on dr t beta r. Now let us take this transformation outside. So we get t of alpha is equal to t of d1 beta 1 plus d2 beta 2 so on dr beta r. Further, this implies t of alpha minus t of d beta 1 plus d2 beta 2 plus d3 beta 3 so on dr beta r is equal to 0 dash. So just we have transformed this term to LHS. Then remove the transformation outside from these terms. So we get t of alpha minus d1 beta 1 plus d2 beta 2 plus d3 beta 3 so on dr beta r is equal to 0 dash. That means this term is mapped to 0 dash. Then this implies that this term belongs to the null space. Hence alpha minus d1 beta 1 plus d2 beta 2 so on dr beta r belongs to n of t. It belongs to null space. Since this belongs to null space, it can be expressed as the combination of vectors in null space. Hence alpha minus d1 beta 1 plus d2 beta 2 plus d3 beta 3 so on dr beta r is equal to c1 alpha 1 plus c2 alpha 2 so on cn alpha n. Because alpha 1, alpha 2, alpha 3 are the elements of the null space. Since the vector alpha minus of d1 beta 1 plus d2 beta 2 so on belongs to n of t, hence it is a linear combination of its preceding vector. So alpha is equal to, we are transferring this term to this side, that is a minus term to this side, that is alpha is equal to c1 alpha 1 plus c2 alpha 2 c3 alpha 3 so on cn alpha n plus d1 beta 1 plus d2 beta 2 so on dr beta r. Now see, alpha is expressed as a linear combination of alpha 1 to alpha n and beta 1 to beta r vectors. Hence B spans U. Then the second property, B is linearly independent. To show that B is linearly independent, let C1 alpha 1 plus C2 alpha 2 and C3 alpha 3 so on D1 beta 1 plus D2 beta 2 so on dr beta r. Now take the transformation of these terms. So we get T of C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 so on Cn alpha n plus D1 beta 1 plus D2 beta 2 plus D3 beta 3 so on dr beta r is equal to T of 0. T of 0 is 0 dash and the T of C1 alpha 1 plus C2 alpha 2, you can write it as C1 T of alpha 1 plus C2 T of alpha 2 so on D1 T of beta 1 so on dr of T beta r is equal to 0 dash. Now since alpha 1, alpha 2, alpha 3 are the vectors of n of t, their images are equal to 0. Hence T of alpha 1 is 0, T of alpha 2 is 0, so on T of alpha n is equal to 0. Hence this equation becomes C1 into 0 plus C2 into 0 plus C3 into 0 so on Cn into 0 plus D1 T beta 1 plus D2 T beta 2 so on dr T beta r is equal to 0 dash. Hence this implies that D1 T beta 1 plus D2 T beta 2 plus D3 T beta 3 so on dr T beta r is equal to 0 dash, which implies that D1 is equal to D2 is equal to D3 is equal to so on dr is equal to 0. Because beta 1 dash, beta 2 dash, beta 3 dash cannot be zeros. They are the images of beta 1, beta 2, beta 3. Hence, which implies that D1 beta 1 dash plus D2 beta 2 dash plus dr beta r dash is equal to 0 dash implies that D1, D2, D3s are equal to 0. Since B2 is linearly independent. Since this is linearly independent, it can be written as the linear combination of preceding vectors. So that is C1 alpha 1 plus C2 alpha 3 plus so on Cn alpha n plus D1 beta 1 so on dr beta r is equal to 0. See, further this implies that C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to 0. Why? Because alpha 1, alpha 2, alpha 3 are the elements of n of t, therefore they are mapped to 0. Hence, these elements cannot be 0, but the scalars along with them C1, C2, C3s are equal to 0. Since B1 is equal to alpha 1 so on, alpha n is linearly independent. It can be written as the combination of C1 alpha 1 plus C2 alpha 2 so on plus dr beta r is equal to 0. This implies that all C1, C2s, D1, D2s are equal to 0. Hence, B is linearly independent. See, from the above results, D1 is equal to D2 is equal to 0, and again we proved that C1, C2s are also equal to 0. Hence, in the linear combination, C1 alpha 1 plus C2 alpha 2 so on, D1 beta 1 plus D2 beta 2 so on, dr beta r is equal to 0 implies that all scalars C1 is equal to C2 is equal to D1 is equal to D2 is equal to dr is equal to 0. Hence, B is linearly independent. So, which implies that B is linearly independent and B spans U. See, both the conditions of the basis have been satisfied. Hence, B is a basis of U. Since B is a basis of U, dimension of U is equal to the dimension of n of t plus dimension of r of t, which is nothing but n plus r. That means the rank plus nullity is equal to dimension of U. Hence the theorem. Thank you.